Hi, everyone. Thank you for having me here. So we're talking about the user of ML Inspect. I think we are one of the user, and we are huge fan about what Sebastian and Stephen have been building over the years, and we're looking forward to actually to more collaborations. So today, let me tell you a little bit about what we are doing, both at the higher level about the structure of my group, and also something about how to debug machine learning pipelines, how to debug data, and also how to debug pipelines, not in generic cases, but also for some machine learning metrics. I think everyone here agree we are in the center of something fascinating, right? So, and probably a revolution of technology. So we see the success story of machine learning really everywhere, from smaller sensors to self-driving cars, even to as big as a smart city. And as a country level, right? So we also have a whole bunch of initiatives. I'm sure Netherlands have a bunch of amazing initiatives, right? So in Switzerland, we have our National Data Center, we have our AI Center at ETH. All of them actually try to take these fascinating technologies and try to bring them to the people. On the other hand, so the good thing about working in a university is we have the chance and the privilege to actually have access to a whole bunch of user base. So there are those people who are really top in their own area and see the potential of machine learning and AI is going to have in their domain. So over the last couple of years, we have been working with actually almost 20 different people, 16 professor and research group across 6 different departments at ETH, and also companies locally, right? So from those dealing with defense, right, dealing with healthcare, meteorology, finance, so on and so forth. For each one of them, we are really lucky to actually look at at least one of their data sets via various ways and try to understand how they see machine learning moving forward and also observe their struggle in using today's machine learning systems. So one question that my groups really want to understand is, given all those success stories that those big companies are doing and all those potentials those domain experts are seeing in real world, what is stopping us today from putting all those technologies into the hands of everyone? So of course, a question like this is rarely a pure technological one, right? So often it's educational. We should keep our university strong and keep producing data scientists for our society. And some of them are socio-economical, some of them are related to regulation. But on the other hand, technology itself is always the foundation for all these important discussions. So in terms of technology side, one thing that we have been really working on is actually inspired by the question people have been asking for hundreds of years, right? That is, whenever there's a new technology, when should it going to be massively democratized? So people have been asking about a question 100 years ago when they try to replace horses with cars, right? So we know how to build cars 400 years ago. If you look at this, it's not that different from the car we are seeing on the street. We keep doing this for hundreds and hundreds of years, but not until the Model T from Ford in 1908 that lowered down the cost by orders of magnitude that we see this mass democratization of this technology to our society. So one argument that I like to make is that if you look at machine learning and artificial intelligence today, they are very, very, very expensive. And we are in a dire need for the Model T of AI and the machine learning. And if you look at where the cost really coming from, it's actually a multi-dimensional problem because it can be expensive in so many different ways. So first one, the computation and storage itself is actually very, very expensive. If you look at those big language models, right, they are taking if you have a single device doing a petaflops, right, it's going to take almost 10 years on that device to actually train that model. If you look at those recommendation model, either from Facebook and something that we are building, it's very easy for them to become 10 terabyte, 100 terabyte just to hold that model. And the ownership cost of infrastructure is not getting cheaper, right? So on public cloud, right? So sometimes with a single dollar, you get to run 40 teraflops for 1 hour, and you get to hold, for example, 1 terabyte of memory, right, inside your inside your machine, it's $7, something like that. If you combine this, it's very easy for you to burn $2 to $4 million to just train that language model, and just burns $20,000 every single day to just holding that model inside memory. And this is just for a single model, right? If you look at the development cost, it's actually not getting cheaper. A single data scientist costs you more than 100,000 per year. right? And also because machine learning highly relies on the data, the cost that you have to collect your data, to clean your data is also pretty high. We have application where cleaning every single image going to cost you $3 to $7, right? Think about doing that for hundreds of thousands of data points. And regulation is going to bring the cost a little bit up, right? Because there's also the compliance cost to all those regulations, dealing with fairness and robustness, and to make sure your application is responsible to the mass application to the society. And also there's operational costs, how to monitor our application, how to test it, how to adapt it, how to scale that to different applications. So if you look at all of these things, right? So the key research mission of my group is really try to bring this down by 10 times. We want to bring what used to take 1 hour to 5 minutes, what used to take 10 labels to do to 1 label. The key hypothesis of our group is once those costs have been decreased by 1 order's magnitude, it will change how people are building those applications. And although it won't solve all the problems about mass democratization of machine learning, but it's going to make some very hard discussions on the socioeconomical and the regulation side much, much easier. So, but this is a super, super hard problem. If you look at why it is hard, there are at least 2 different reasons. The first reason is that if you look at all those costs, they are actually intermingled in 2 different ways. So the first way is all those costs, they are not independent. How fast you train a model, the computation cost, going to have a huge impact how people are going to develop those models and have a huge impact about how expensive it is to actually be compliant to all those regulations and how to operate. On the other hand, every single change on the regulation side going to have an influence on what type of model you are going to train and how expensive those models are. To really make progress in tackling this cost, we need to take a holistic view on these problems. And the second thing that tackling this problem is actually challenging is they are also intermingled in the way that we have to take a holistic view of technologies and methods that we are going to bring in together. Because many of this relies on decades of study of data management, of system and hardware and machine learning. You cannot make progress by focusing on one type of technology. You cannot need to bring them together into a single framework. So it's super hard. I have no idea how to answer this question, but over the years, my group have been focused on 2 very specific scientific questions. So first question is by looking at this model training process and try to take every single bit that we are communicating through the network and every single floating point operation we are doing when training such a model, every single synchronization barriers we are enforcing such that the machine wait for each other, every single data movement and shuffling we are doing inside our data system, and every piece of data that we must hold inside our memory, and every fast connection we are building between those devices. We want to take this every single thing that make building machine learning training really, really expensive and try to ask, are they really, really necessary? And if they are necessary, how can we design new hardware to actually make them cheaper? If they are not necessary, how can we design new algorithms and how can we change our data ecosystem? The second scientific question that we have been really trying to understand is we want to take this development and regulation compliance and operational process and try to understand whether we can make the process of improving the quality, either accuracy or fairness or robustness of single machine learning model as systematic as possible. Can we make the continuous testing of the quality and also the adaptation of machine learning model to different scenarios as systematic as possible? So given this, we actually make some of the progress. For the first question about the training cost, right? If you look at all those things that are making machine learning training expensive, not all of them is actually necessary. By actually co-designing this algorithm, by co-designing the data ecosystem and also the hardware, you have at least 1 order's magnitude speed up here for you to cash in. So we have been playing with a whole bunch of theories. If you're interested in this, this is a book about this theory. And it actually allows us to do some really interesting things, right? For example, at some point we train a recommendation model with 100 trillion parameters, right? Probably the biggest one to our best knowledge. And some of the things you can actually play with in the open source environment. If you using PyTorch Lightning, right? So you can actually enable a whole bunch of training strategy with a single line of code. If you are using OpenGauss as a database system, right, you can train some machine learning model with a single line of code. Of course, there's a whole bunch of open source things that you can actually play with. And for the second question, right, so the thing that we realize is for many of those processes, you can actually make them very, very systematic. And there is at least 10 times saving that you can have if you get your user in a strategic and systematic way. And over the years, we have been looking at this kind of end-to-end process of building machine learning applications, all the way from data ingestion to augmentation to data cleaning, acquisition, and to AutoML to continuous integration and testing and adaptation. So today, let me talk a little bit about very small components in this picture. It's about data cleaning and data acquisition. And going to touch 3 different costs, as you are going to see. The development cost about building machine applications, the compliance cost to some of the regulations, and also to the computation cost. And key scientific question we really want to understand is actually, we have these 2 dimensions that people have been working on over the last half a century almost. There's a data quality problem, there's a machine learning quality problem. How can we reason about these 2 things in a joint way? So before I talk about this, how people are building machine learning applications today? If you want to get one machine learning model out of some system, it's actually very easy to do today. Now you can take your favorite cloud storage providers, they all give you something called AutoML, right? So in Switzerland, so we have the National Data Science Center who built a very interesting system actually called Rinko. And we actually start to integrate some of our things into their system. So it's actually very easy to train a model today, right? You have your whole bunch of data set, and probably all you need to do is just 2 different commands, right? You import your data, right, from some of the data system, right, into your machine learning system, right, with 1 single command. And then with another command, you can say, okay, just do AutoML on this data set. And system going to train a whole bunch of models, right? And then you can go back a couple minutes and check the process of training, right? So as you can see, just in a couple of the minutes, right, you can get a model with a reasonable accuracy. So this is not hard anymore today. But what is next? And that is something that we are really curious about. So once you have a model, there are multiple questions you need to answer. The first one is, what should we do if this model is actually not good enough, right? And what is the reason that this model is not good enough? And what is the most important problem that I should fix to improve the quality of this machine learning model? So, and then that become a little bit tricky because there could be so many different types of problems. So let's take this canonical view about how machine learning is being done today. On the left-hand side, you have the training data, you pipe that through a machine learning training process, you get a machine learning model. And you can measure some quality of this machine learning model, either accuracy or fairness. But this is actually not what happens in practice, because in practice, your data is never as beautiful as this. It could be a whole bunch of data problems. There could be missing value, there could be wrong value. And if you look at database literature, we have this beautiful 4 different dimensions of data quality that people have been working on over the years. And there's clearly a mapping from the data quality problem to the model quality problem. For example, if your data quality is not good enough, right, you have a lot of noise, highly likely your model will have low accuracy. Right? If your data is not complete, you are missing some critical mass in some of the population, highly likely your model will not be fair. And this is something that you can actually quantify. So this is actually one paper we have at ICD 3 years ago, before people keep talking about this data-centric thing. So what we realized is that if you take one data set, which is dirty, you can try a whole bunch of machine learning models. And for each one of them, if you think about the F1 score, right, as the metric of the quality of the model, you can see first one, different machine learning models actually make a difference, right? Some of the models are not that good, some of the models are really good. But one thing that you can realize is all of them stop at this magic number, 76% of F1. And no matter what you do on the machine learning side, it just cannot get higher anymore. But the moment you just clean your data a little bit, you get this huge jump in the quality. right? So as you can see, there are actually two different ways you can improve this model quality, either by keep training different models, but you can also improve that by changing your quality of your data. And often the best way to improve your machine learning model is to improve your data. But for many of our users, this is something that's very easy to say, but very hard to do. Why? Because if you look at this picture, there are so many different ways you can improve your data set. You can get more features. You can clean some of the outliers. You can get more data. You can clean some of the cells or fill in those missing values or fix some of the wrong values. So there are so many things that you can do. Given a table or training set with millions of examples, users are often overwhelmed by the amount of possible operations that they could conduct. And second, not all those operations of making your data better actually matters for machine learning. Sometimes machine learning is going to automatically fix some of the noise inside your data. And it's not very rare for us to see users fixing a whole bunch of things in the data set. They retrain the model. At the end of the day, nothing really happens on the model side. There's only those very small amount of critical data problems that are hidden in this ocean of data problems that we need to find for our user. And also the feedback loop today is very, very long. After you fix your data set, you need to retrain your machine learning model, and that could take minutes or even hours for you to get a single bit signal that whether the data operation you are doing actually matters or not. And what makes things even worse, if you look at the machine learning application today, it's often not about machine learning. There's only small components in the machine application is actually training a model. And the majority of this program, as you see, is actually dealing with feature extraction and data transformations. And putting all these four different struggles all together, so most of our users that we see are actually wasting their times fixing data problems that often do not matter at all. So they need help. So one thing that we really want to do is to imagine, wouldn't that be nice if every single Jupyter notebook that you have after developing your machine application have this magic button called debug. And once you click that, you say debug fairness. And we tell you, okay, so these are the lines of code that's making your machine learning low quality, unfair, or not robust that you should look into. Wouldn't that be nice if every single AutoML system have this magic button called improve data? And once you click that and select the thing, the model quality dimension that you want to improve, we have this magic list of data examples ordered by importance and say, okay, if you really want to improve your model accuracy, these are the data example you should look at because they are hurting your model. So this is what we want to build. But again, there are a lot of hard technical problems that we have to tackle to actually make this tool functionality happen. So this is a technical problem that we want to understand. On one hand, you have your data set. You could have a whole bunch of problems. Some noise right, in your data, some missing value, and you pipe that into a feature extraction pipeline, and then you train your machine learning model, you get a model, you measure some of the dimensions of the model quality. The thing that we want to understand is whether we can compute several notions of importance for this data example to really understand whether how important each of these are to improving your final machine learning model quality. And also for each operators within this feature extraction pipeline, can we assign some notion of importance, right, to really understand whether they're hurting me or whether they're helping me. If you look at this, there are three fundamental questions that we really want to understand. The first one is how can we define the notion of importance? This is a very hard problem because we are actually trying to compressing this very complex problem of model quality into a single dimension number, right, associated with each of these example and each of those operators. And second, how can we enable real-time interactions? We want our computation to be as fast as possible, right, to make sure user can do this iterative data debugging loop as efficient as possible. And third question is actually, okay, once we have those importance, how can we use them? So let's go through this one by one. How to define importance? So this question sounds a little bit trivial, but if you think about it, it's actually not that easy to do. So let's look at one very simple example. I have this 4 different training example in my relation. And then I say, okay, how important is this red tuple? Well, how can we do that? The most natural way maybe is to do some intervention. We say, okay, you want to understand how important this red tuple is. Let's try to compute the accuracy you have on this whole data set, and then let's try to remove it. And then I can get some improvement by actually adding this red tuple into my data set. And this can already tell you a whole bunch of information about how important this red tuple is, right? And there are actually many work use this importance, right? So as your notion. But what's the problem of this? The problem of this is actually can be very suboptimal. It's not that very hard to see by just looking at one example. Assuming you have these 4 tuples, 2 of them are bad tuple and 2 of them are good, okay? And my utility function, my accuracy, have the following structure. That is, once I have a bad tuple in this data set, then I have a very low utility, like -1. Only if I have all those good tuples there, right? I have a very good utility. For example, if you look at this, if you think about, okay, what is the value of this kind of bad tuple, bad red tuple, right? In this case, you are taking the difference between these 2 different data sets, and then you get 0 because both of them have a bad tuple in it. If you actually say, okay, then what is the value of this good tuple, right? You get something like this. So as you can see, this leave one out notion of importance could be very confusing, because if you use that to highlight these data problems, both this bad example and this good example have exactly the same influence to your final score. So essentially, whenever you have this strong correlation between those examples, which is usually the case in practice, using this leave one out notion of importance could be very confusing. So what should we do? Right? I mean, there are many things that you can do, right? You could actually consider all these different ways you can subsample your data set. And for each one of them, you add in your red tuple and compute this collection of improvements. Then you can aggregate them in certain way, right? And then you can use that as the answer of your importance. So if you kind of aggregate them by having this uniform weight for each of the possible world, you get something that is really closely related to multilinear extension. And people have been shown that in combinatorial optimization, it actually works really well in many cases. If you actually aggregate them in another way, you get Shapley value, right? Which is have a very interesting game theoretical foundation, many good properties, and works well in many cases. So if you look at these 3 different importance, there's actually some interesting dedicated relationship between them, right? So it's just something that our fascinating student just proved like last week, right? If you look at these 3 different notions of importance together, right? So there's actually a very interesting trade-off. Sometimes you should use uniform weight, and sometimes you should use Shapley, right? Depending on different things. But almost always the case in many things, they are actually almost always better than this leave one out notion of importance. And that is actually something you can actually see in practice. This is actually one application that you actually try to highlight different data operators inside your feature extraction pipeline using those importance. So your x-axis is that you follow the most, follow the importance from the highest to the lowest. And for each one of those operators, you try to fix them. You try to change them in something that can improve your final accuracy. So as you can see, when you have this a single change, right? So leave one out is very hard to beat. It's almost by definition the best thing that you can do if all you want to do is to fix one operator to get better accuracy. But once you fix those multiple operators, you can see this almost 30% accuracy gap between uniform aggregation Shapley over this leave one out notion of importance. So essentially how you pick this important metrics really matters for you. And then you can actually have different notion of importance if you care about different ways to fix your data. So in previous example, we cared about essentially the importance of every single tuple, but you can also start to reason about importance for every single cell. Assume you have a data set look like this, and for every single cell, you have certain uncertainty, right? It could take multiple different values. So, and then over this uncertain data set, you train a model, you get some metrics, and then we try to understand, yeah, so what is the impact of all those 30 cells to my final machine learning accuracy? What is the importance of this cell once I know some noise model? And this is going to give you a very different notion of importance compared with the previous example. So, and that goes back to a very beautiful theory in database about information processing over uncertainty. And you don't need to go really far to find such example, and they are in your database book. And how does our database people think about uncertainty, right? Well, we just put them as a special state called null, right? For example, in this example, you do not know the age of Kevin. What should you do in database? Yeah, you put this very special state to say, hey, I have no idea what that is. And then once you answer some SQL query over it, right, you will have this very special algebra to say, yeah, if you compare null with 30, my answer would be unknown. So the fundamental curiosity that we have is whether we can apply this also to machine learning. But before we do that, let's try to understand a little bit deeper about what database is actually trying to do. Because what it's actually trying to do is kind of interesting. On one hand, you have this relation with a whole bunch of uncertainties, and then you want to answer some data processing query over it. The thing that you could do is to actually enroll it into a whole bunch of possible worlds. Each one of them contains one possible value for this unknown state. And then for each of these possible worlds, you do the SQL query, you get your answer, and you only return things that you are certain is going to be there. So in other words, whenever we are using our database system, the answer is actually robust in a very precise way against uncertainty and noise in the input. So there's nothing stop us from doing this for machine learning. So assuming you have an input training set with a whole bunch of uncertainties in the value, and then you want to train a machine learning model here and predict that on some tuple, the thing you can do is you can actually enroll that into a whole bunch of possible worlds. For each one of them, you do the same thing. If the machine learning model gives you yes in all those possible worlds, yeah, you answer yes because you know it's true. No matter what noise you have inside your input, the machine learning model always going to give you the same prediction. If all of them is no, you get no. If they disagree, you get no, right? So you can also aggregate them in a softer way. You can compute the expectation, you can compute the entropy. Once you have this view about training machine learning over uncertainty, it's very easy to design some notion of importance about that cell, right? A cell kind of uncertainty is kind of important if knowing that value can bring down this uncertainty as much as possible. So another way that you can design this cell level importance is to use the expected decrease of entropy. So a lot of things that you can do in actually designing those important metrics. But the second question is, once we design these important metrics, how can we compute them? There are two fundamental challenges that we are facing. So first one is for many of those very beautiful importance notions, they are very hard to compute. Just think about entropy, right? You have a data set with a whole bunch of noise. So what should you do? You need to enroll them into a whole bunch of possible worlds. For each one of them, you train a single machine learning model. So there are exponential many of those possible worlds and exponential many machine learning models that you have to train. On the other hand, if you look at sharply and expected improvement, right, you need to consider all those combinations of tuples. Again, there are exponential many of them, and for each one of them, you need to train a single machine learning model. Clearly, it's quickly become very infeasible, and we have to do something. The second challenge is that machine learning pipeline could be a very complex piece of code. Because as I said, there's only small components is about learning, a very large component is about data transformation. And although people have been looking at how to compute many of those importance for single machine learning model, we are lacking this fundamental understanding about how to bring these two areas together, how can we connect these decades of data management study about data performance and these decades of study of machine learning about data importance with the joint analysis. So that is what we have been doing in the last couple of years. So here's what we know in this area. First one, we know that if you try to understand this end-to-end pipeline, it could be very, very hard to do. But once you can do is you can actually approximate that in certain way. You can approximate your noise model into cost table. You can approximate your feature extraction pipeline into a positive relational algebra query with very beautiful positive data provenance polynomial. You can approximate your machine learning model into a simpler classifier. So once you have done this, many of those problems becomes easier. So in general, if you take this machine learning pipeline, right? So the thing that you are going to do is you take this feature extraction pipeline and compile that into a polynomial in the provenance semi-array, maybe with MLinspect, right? To describe the data provenance of feature extraction. And then you replace your machine learning model with a simpler classifier, for example, K-nearest neighbor classifier. So there could be a different shape of the feature extraction pipeline. You can have this one-to-one mapping that we call MAC pipeline. You can have this one-to-many mapping if you have data augmentation that we call fork pipeline. You can have this one-to-many joins when you try to bring information all together. What's actually very interesting is that if you look at this proxy pipeline, many of the fundamental quantities like Shapley, expected prediction, or like entropy become in polynomial time. It actually depends on the shape of your feature extraction pipeline. If you have this one-to-one mapping, you can have a very, very efficient algorithm. When you have a different shape, the whole thing becomes a little bit tricky, but still in polynomial time. So this is actually something that really surprises us and also make us extremely excited, because that means for many of those machine learning pipelines, we do have a very efficient way to reason about this fundamental quantity. And second lesson, which actually surprised us in the beginning, is it actually works. If you look at the quantities that computed on this proxy pipeline and use them to debug this original pipeline, they actually work. So how can we use this, right? So this is actually one example. Assume you have the training set with incorrect labels, right? Some of the image which is cat labeled as dog, for example. You have your machine learning application, and then the question is, how can we find out those training examples that matters for my machine learning model? You could compute the Shapley, and in expectation, they should have very small and often negative Shapley value. If you follow this importance, right? So you can actually get a data cleaning strategy that's very, very efficient, like almost 3 times more efficient than the random strategy in improving your machine learning accuracy. And another interesting thing is you can also have different utilities. You can not only debug for accuracy, you can also debug for fairness. So this is actually one example where your data noise have some unfairness property. If you just clean your data, right, in a random way, which is what people usually do. If you look at the evolution of unfairness, you can see the moment you are trying to improve your model accuracy, if you are not being careful about robustness, your model could be more and more unfair during the data cleaning process. But you could also try to have data cleaning strategy, try to maximize your fairness by using fairness as the final utility function of your model. So here you can see, you can have a data cleaning process that improves your accuracy really fast as all the other strategies, but has really, really much better fairness compared with all the other strategies. On the other hand, it's also much faster. So you can also use this to improve the robustness of your model. So this is a very interesting attack that people have in practice called backdoor attack. Right? What people do is they try to embed those spatial patterns into your image, and then you train a model. And then during test time, if you have another image with the same pattern, right, you are going to make an error. So once you can do is you can actually try to identify the Shapley value of those examples, right? Often, if you look at those things with negative Shapley value and try to remove them, right, you could have a data cleaning strategy that improve your robustness of the model much faster than a random strategy. And this is also something you can do for data cleaning. Right? Assuming you have a data you have a training set with a whole bunch of noise, and then you have a clean oracle to tell you, okay, so this is the right value for this cell. If you follow this decrease of entropy, right, you can actually have a data cleaning strategy much more efficient than the random one. So this is also something that you can already play with. So there are multiple implementations, right? One is actually by Sebastian and Stefan, right, into their August system, right? Another is Boyan, I think Boyan is on the call, right? Implemented some system within our system called Datascope, right? It's very easy to use. You have your end-to-end machine learning pipeline. You say, okay, this is my pipeline scikit-learn, and this is the utility that you want to optimize for. And then with a single line of code, you get the importance of all those training examples. But one thing that's interesting that I actually want to emphasize is that if you compare these two systems, ArgusEye is way better than Datascope. So, and then here's the reason. There are actually two reasons. First one, Sebastian just built better systems than I do, which is definitely true, okay? But second is a fundamentally technical one, is that a principled provenance system is very, very important. The reason that ArgusEye is faster, more robust than Datascope that we build by ourselves is that ArgusEye takes advantage of ML inspect, because you have this principled way to describing and managing and also query over data provenance. You are able to implement all those higher level functionalities way faster than we can ever do by ourselves. So to be honest, I think this is something that our community should appreciate more, the importance of this basic architecture about provenance management and this huge influence to higher level applications. So this is actually what all I have for today, right? I talk about this very small piece about how to improve the development cost and also the computation cost, right, in this picture, but there's a whole bunch of things that we could do, right? So I think this is a very exciting area, really looking forward to discuss with all of you guys. So I will be here until Monday, right? So if you want to meet in person, right, I will be here, right? Yeah, so that's it. Thank you guys so much. I'm now happy to answer your questions.